The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So if I give a very quick summary of what we're talking in the first lecture, we reviewed the first and second law, and of course, I assume that you all have seen in various courses, and this is the maximum thermodynamic efficiency of any heat engine operating between two heat reservoirs. One is cold, the other is hot. So that's the key points. And then for many of you, probably first time, is I introduced, if you go to the statistical side, the microscopic picture, at one quantum mechanical state, you count how many particles, either electrons or molecules or photons or lattice vibration photons. And for electrons, it's given by Fermi-Dirac distribution. And where this mu is the chemical potential. That's the energy you need to take a particle in or out of the system. And E is the energy of that quantum state, and T is the temperature. And then say that's for electrons, where the Pauli exclusion principle, or say the maximum possibility of having an electron in a quantum state is 1. So this number is between 0 and 1. And then I introduced also the other type of particles, those the photon, electromagnetic wave, or lattice vibration, we call photon, or even molecules. This is the Bose-Einstein distribution, where, again, this is the energy and the mu is the chemical potential. But here, we're not limited by the Pauli exclusion. So in one quantum state, this number can be larger than 1. And if you take out this -1 or +1, you go to the classical regime, where we call the distribution F. Doesn't have that one, the exponential distribution. That's the Boltzmann statistics, Boltzmann distribution. This is what you see in Arrhenius law in chemical reaction. So that's a review of thermodynamics. And then I went down to heat transfer, where we have 3 modes of heat transfer. The first mode is heat conduction. The Fourier law tells us the heat flux is proportional to the thermal conductivity and the temperature gradient. But I went one step further to show you in a very simple kinetic picture, just count the number of molecules going from left to right and right to left. Then we have a simple expression for thermal conductivity. That's 1/3 C is the specific heat, V is the velocity, and the gamma is the mean free path. That's how long the molecules travel. So this is the heat conduction mode, and then we have the Newton's law of cooling for convection, where the heat transfer is proportional heat transfer coefficient, area, and temperature difference. And the difference is this heat transfer coefficient is no longer a property of the material. Thermal conductivity is a material property. And H depends on the flow configuration, natural convection, forced convection, what kind of geometry. And then the third mode of heat transfer was thermal radiation, and I gave the Stefan Boltzmann law. That's the maximum emission for an object can have in the. So this is called the Stefan Boltzmann law. It's proportional to temperature force power. A real object, the emission is less than that. So we normalize the real object emission by this number. You get the so-called emissivity. That's it's a number between 0 and 1. So I moved on at the end of last lecture. I was trying to show you the thermal radiation can be derived and here I'll continue and give you a derivation of the Planck's law. Again, now we move from continuum to a microscopic picture. And once we go to microscopic, I use the same strategy. I'm going to do the counting. The number of modes, quantum mechanical state, because I already know from statistics, each quantum mechanical state, how many photons. That's the Bose-Einstein distribution. That's the previous slide here. So I know each mode, this is the number of, at this temperature, that's the number of photons in the modes. And also I commented before for photon, this mu equals 0. So we'll use that, and the task is really just count the number of modes. So I will take a qubit, and I assume that the wall is perfectly reflected, and this is at a temperature T. And now I want to see how much radiation energy is contained inside this cube by counting the modes. I want to show you this because we will actually use a lot of those counting techniques towards electrons, towards the photons. So it's a general way of doing the counting. And of course, we have, it's an electromagnetic wave, so here are basic relationships, and you know the wavelength times frequency equals the speed of light. So I write it rather than wavelengths, I write it in terms of wave vector is the inverse wavelength, and angular frequency, so omega equals it's a linear relation between the amplitude and the of the wave vector. Wave vector is vector, so it's kx, ky, kz in Cartesian coordinate, and that's what we call the dispersion relation. The relation between wave vector and frequency is dispersion. So now I want to see how many modes in this cavity, and then my simple picture is this is the length in the x direction, and because the perfect wall, so it's reflecting and it's a wave, so the only way that this wave can exist is having zero amplitude at the end of the on the surface of the wall. So this is if you have a string and you do the go to think about you play violin, and you have the notes at the two ends and the vibrational modes at the two ends 0. So we have different modes. The first mode is a half, and the second mode is including the full period, and I can use this as my constraint. In the x direction, that's the length, and half modes twice or n times the half mode, half wavelengths. So with that, I go to, because the wave vector in the x direction is just 2 pi over lambda, so I can write this in terms of n and Lx, the length of the box. And if I can write kx, I can same way to write ky and kz. So I have allowable numbers for this kx, ky, kz. And then each set of kx, ky, kz, right, if you think about the wave, give me a distinct wave. And that's one mode. Except in electromagnetic wave, you learned before, it's a transverse wave. The sound wave is a longitudinal wave, right? When I speak here, I'm pressing the air, and the direction of propagation of the wave is in the same direction as the air, say, doing expansion and contraction. So that's a longitudinal wave. The transverse wave, electromagnetic wave from the sun, that's direction to the earth, the k vector. But the electric field, the magnetic field is perpendicular to the direction of propagation. And I have 2, so I put a 2 here. And then I sum up all the modes. So n number, each set of n number, nx, ny, nz, is one mode. So I count how many modes there are inside this cavity. So I just sum up all possible combination of n. Each one combination is 1 mode. Each mode has two let's say polarization, vibration direction, and each mode, the photon has an energy. Every photon has an energy h omega. Yes.
Yeah, I have a question. How does the factor 2 relate to the fact that the electrical field is transverse to the wave vector?
So when I have one set of nx, ny, and z, so in one case, the electric field is this direction. In the next case, is this direction. All other is a combination of the two, so it's not fundamental mode. So you have factor of 2 is because in this one set of nx, ny, and z, you can have two possible E directions, electric field directions. So I do my summation here, and the only thing, this is the trick I will use many times. I don't like summation because I don't know how to do it easily analytically. So I'm converting that summation into integration. Right? So if I think about the n are discrete and the wave vector discrete, but if this separation between the energy is small enough, so I can say in this distance dkx, and this is the unit of this discrete, so that's equivalent to a continuous number of n, rather than discrete number n. Right? So this is the equivalent of summation into integration as long as this function doesn't change a lot between every two n's. And I do that for y and for z. So this is this step is just for my future. Okay. What this step means, rather than doing this factor of 2 here, from 0 to infinite, which is a standing wave, okay, n is a integer, positive integer. It's a standing wave. I'm going to do from negative infinite to positive infinite because this is a even function, okay? And this way, I'm really, rather than, so what I miss is this factor of 2. I don't have factor of 2 anymore. And physically, what I'm saying is this standing wave summation is the same as 2 propagating wave, counter-propagating wave. When kx is negative, it means going negative direction, positive goes to positive direction. So this is mathematically equivalent, and later on I'll do a lot of this minus infinite to plus infinite summation rather than just do standing wave summation. Right? So it's more mathematics. I can walk you through, but there's no physics here. It's a book content doing the lever. I already did the dkx, dky, so I wrote it into Cartesian coordinate. Now it's not x, y, z, it's a kx, ky, kz, it's Cartesian coordinate. And three-dimensional integration, the rest is just the numerator here I had before. Those numerator Lx, Ly, Lz, right? So 8 pi cubic. So that's just copying what I had before. And h omega f is still copying. So I'm doing all the copying. Now, to simplify life, the integration, you can say I have a conflict. The conflict is y is integrating over k, but my function is a function of omega. So I have to transfer either y into omega into k or k into omega. And I would like to transfer k into omega in this case, and it's your choice actually when you do it. So I transfer that k into omega, and I want to do spherical coordinate because that's easier. Okay? So dk dx, dk x, dk y, dk z is 4 pi k squared dk in spherical coordinate. And now you go to look at the kx squared, right? I hope I've written down, okay, in the previous slides. Okay, kx squared equals omega squared divided by c squared. So this is how I change k into omega. That's where the dispersion relation, the relation between omega and k is very important. Okay? So K into omega, that's just omega equals say K. So dk is d omega d over c. And now I combine everything. I do per unit volume how much energy we have. And I write all those other factors into the integration. And this is what I have here. Everything is math. And this D, I call it density of states. What it means is how many quantum mechanical states or electromagnetic modes we have between around omega. Okay? And so this is the photon energy, one photon, one state, how many photons we have, and then in this state, in this region, how many states we have. Right? So this is also the energy density. I write everything together. It's just energy density at this frequency. Okay. So this is the energy density as I wrote down. And if I want to write it out, density of states, F, and the H omega is combined. That's Planck's law. Planck's black body radiation law. The energy density per unit volume. And these were actually the start of quantum mechanics. Okay, Planck was trying to explain the black body radiation. And if this is not called, say, because the energy states, in fact, most of the time we don't talk about energy state, we talk about radiation leaving a surface, not just how many energy in per unit volume. Okay? And in that case, the definition is the intensity, energy flux per unit solid angle. What is a solid angle? A solid angle is if you have a two-dimension, you know a polar angle, xy. From xy, you want to use a circle, polar coordinate, you have polar angle. And in three-dimension, that angle is a space, angle in space. That's a solid angle. It's per unit area, normalized the distance r squared. So a sphere, the area is 4 pi r squared. Right? The solid angle then is 4 pi, because r squared cancels. In 2D, what's the phi? 2 pi. 2 pi versus space 4 pi. That's the solid angle. So because that's the terminology we use often. So this intensity is just now, I know the energy density per unit volume. This energy is propagating at the speed of light, right? So is energy density times C, and it's going radiation, thermal radiation is going all directions. So per unit solid angle is 4 pi. So this way, I write the speed of light times energy density divided by 4 pi. That's the intensity. And this is just you go continual substitution. You get the intensity. And sometimes we do per unit wavelength interval rather than per unit frequency interval. So rather than doing d omega integration, you do d lambda integration. And because lambda is times omega equals 2 pi c, so you convert the omega into lambda. Again, this is when you actually take a radiation course, this will be the Planck's law that's written normally. And so that's a per unit solid angle. And when I do the total radiation per unit area, so this is the per unit the area times area. So that's the total radiation is a pi times I. That's the mathematics. We're not going to get into it. What I want to show is from here, if you do your integration, you get Stefan-Boltzmann law. Okay, Stefan-Boltzmann law. If you take a 255, is where we start on thermal radiation. And what I give you is a way of going from basic concept to go to the Stefan-Boltzmann model. But say what's important is for you to look at the curve of black body radiation. This is very much relevant to the way we want to do solar cells or solar thermal. Because the sun radiation is about 50, here I wrote 5600, but it's really around 5800 Kelvin. That's the solar radiation. It's like a black body. The spectrum is very similar to this curve. Okay, outside the atmosphere, if you go to measure the solar radiation, it's close to that 5800 Kelvin curve. And at 300, I didn't plot, 300 Kelvin, this peak will be around 10. So here you can see the peak starts decreasing, and that relation is the wind displacement norm. Wavelength times temperature is about back of the envelope 3000. If you don't remember that detail, whether it's 2898, and in fact every time I go back to check, I remember it's about 3000. Okay? So 3000 micron, and that's why our eyes are sensitive to 0.5 micron. We live in the solar system, and the solar radiation, if you put about 6,000, 3,000 divided by 6,000, our eyes, the evolution chooses us to be most sensitive to the peak of solar radiation. Right? And during the night, there's no sun. Everybody is emitting, you're emitting, I'm emitting. We're emitting 10 microns. Right? 300 Kelvin corresponds to 10 microns. Of course, if you take a detector, you can look at it. Right? Soldiers like that. The infrared radiation measurement. But if you look at just a common, a solar cell, right? Silicon solar cell, the wavelengths that they can take, the shortest wavelength is about 1.12 micron. So it's about 1.12. So this is 1 micron, this is 1.12. So only radiation in this range can be utilized in solar cells. You have a lot that's wasted if you do silicon solar cell. This rest of the wavelength energy cannot be used to generate the electron holes. We'll talk about that later. Okay, so that's completing what I was talking in the review in basic heat transfer and the thermodynamics. What I'm going to move on is giving you a brief introduction of thermoelectric energy conversion. In the last lecture, you have seen a basic demonstration of thermoelectric generation. And in fact, this is the module that used to generate the power. I'll toss around. Take a look. And basically here, we are using direct energy conversion. We're using electrons or holes. In semiconductor, we have names for positive electron and holes. And we're using this as a working fluid to carry heat around from one place to another. So let's look at the phenomena, basic thermoelectric phenomena, and then we'll do a simple analysis of that device and pass it around, and then look at the current and the potential application. First, the thermoelectric effect is not new. And in fact, these were about the same time people started to investigate electricity. And Seebeck discovered that in 1821 that when he put the two metals actually as a junction, and the one side is hot, the other side is cold, we measure the voltage. Seebeck, now we call it Seebeck effect. And Seebeck himself, actually, if you go to read the history, he didn't know what's going on. He thought that was a magnetic effect. Because at the time, there are a lot of interest in magnetic Faraday or the experiment. So he thought that was a magnetic effect. And about 10 years later, Peltier discovered another effect. That's the same two, kind of junction, two metals. You pass a current through it. Actually, one side cools down, the other side heat up. He couldn't make ice at the time. Okay. In fact, Seebeck, if we choose his material to make a device, even at that time, a power generation device, you will get about a 2 to 3% efficiency using his material. Nobody built a power generator, so at the same time, people were starting to develop electrical motors. You can say the history was really interesting. So if this one actually worked out first, there will be a lot of studying it, and it will be different, right? Let's say this effect is reversible. You just pass a current first. One case, one direction, it will be cooling, and the other direction, it will be heating. And so both those were experimental discoveries. Thomson did a theoretical prediction. And Thomson's prediction is that based on the experimental discovery and his understanding of the effects, he predicted that when you have a material, one side is cold and the other side is hot, so a material under temperature difference, and you pass the current through it, there will be heating or cooling along the material. So this is not jar heating, okay? Jar heating is always heating. This is reversible. It will be either heating or cooling, depends on the direction of the current. That's a Thomson's. Thomson is also Lord Kelvin, and you'll probably see a lot of Kelvin work, Kelvin relation for this, Kelvin relation for that. He published more than 500 papers. Very productive in his lifetime, right? So now let's get a very intuitive picture. We have to go to, for those understanding, we have to go to microscopic again. And we now have to look at electrons. Let's look at the electrons. And I'm going first to just look at the isothermal. There's no temperature difference in the material. Or isothermal conductor, there are a lot of electrons inside. And apply an electric field, the current will flow, right? We all know that. So I have a current flow. Now, again, I'm doing number counting now. This number, what's the current density? Current density is amp per meter square, is the charge per electron, right? Times per unit volume, how many electrons I have, and times the velocity of those electrons moving. It's very intuitive, right? So you go to look at the unit, it will be amp per meter square. And the velocity is related, I'll give you the relation more later on, through an electrical field. And the coefficient, proportionality coefficient is called the mobility mu. Relating the velocity of the electron to the electric field. Again, this I'll give more detailed derivation. And of course, that will be the Ohm's law. The current is proportional to electric field, and the proportionality constant is the electric conductivity. And sometimes we don't talk about conductivity, we talk about resistivity, just 1 over the conductivity. So this is the Ohm's law, and all the definitions, their units, given here. So this is when we talk about the electrical flow, we typically care about current. But each charge also carry heat with it. I can do the same thing for heat, right? So rather than the charge, electron charge, I'm going to say the heat carried by each carrier. I don't define how I write that heat yet. I'm just saying per carrier, Q is the heat carried by each charge. Again, number density, velocity, the movement. And of course, I can replace NV by J, the electric current. So now the heat current is proportional to electric current, and the proportionality constant is the Peltier coefficient. Right? So associated with the current flow, there is a heat flow. So Peltier coefficient can be defined for each individual material. You don't have to have a junction. The junction is only when you do experiment, how you observe it. Okay? So this is the, when I want to observe the Peltier effect, the best way is to put a junction there. I have two different materials. And when I pass a current through, then you can say the current has to be, electric current has to be continuous. That's a Lambert, right? Electron Lambert, in and equals out. So that's the continuity, current continuity. But the heat carried by the electrons in one material could be different from the other. So if I do my first law of energy balance, I find out if I have more heat flow out, then comes in, I have to supply the heat. So what does it mean, supply the heat? The lattice cools down. The atoms cool down, because I'm talking about electron, right? The atom can supply the heat to the electron, cool down the junction. So this side can cool down, and then on the other side, you'll have to reject that heat. Energy balance. Right? So this is the Peltier phenomenon you observe experimentally. And then you can say, if I reverse current, this phenomenon also is reversed. So this is the Peltier effect. Okay, it's reversible. Now look at the Seebeck effect. Here's the seat here. Okay, Seebeck effect. Right, Seebeck effect is the voltage generation under temperature difference. And you think about, we have charge in the conductor, and then when one side is hot, the electrons near the hot side have more energy, right? The more violently. So they will diffuse to the cold side. So you have, at the end, after diffusion, you have more electron here. When you have more electron, the electron imbalance will happen. You have an electric field building, right? The internal electric field will resist the diffusion. So at the end, you have a steady state where the diffusion current balance the electric field will drive the current back. So this balance will give you the Seebeck voltage. That's the process here. Okay, the Seebeck voltage is defined. I put a lagging sign. This is when you do an experiment. You want one side is hot, the other side is cold. You put a probe. Normally you say, okay, like the definition, I put a hot probe on the high temperature side, positive voltage on the high temperature side, negative voltage on the low temperature side. And if you do that, here it's written very clearly, you should have put the negative side in front. That's the definition. I remember first time I measured a sample, I just got the wrong sign. I didn't know why. Everybody measured differently. Because people normally just say Seebeck voltage is the voltage divided by delta T. But then when you do experiment, you have to see which side is positive. Okay? Thomson effect. What Thomson effect is when you have a temperature difference and then you flow a current through. And then if you look at every point, there is a Peltier coefficient, right? The Peltier coefficient can depend on temperature. So that means when current flow in, the energy carried in could be different from the energy carried out. So the heat carried out could be different from carried in, and then that difference must be made up. Cooling by either cool or rejected. So that's the Thomson effect. And Thomson coefficient is defined the local amount of heat absorbed or rejected versus the gradient divided by temperature gradient normalized as the current. That's the Thomson coefficient. Okay. So we have this phenomenological, very kind of waving explanation. And now I want to do more detail. I want to put this into more mathematics into it. Oh, I forgot to mention here. Kelvin, of course, Thomson. Well, Kelvin realized, based on his understanding, those three effects are interrelated, and he actually gave the relation between the Peltier coefficient in Seebeck times temperature, and Thomson coefficient is the Seebeck derivative with respect to temperature. Okay, those are temperature-dependent properties. Like I said, let's go. Let's go next to the device, and we want to say, based on this, what are the material properties I want? So I show this device, and again, it's you can buy it commercially. Particularly, some of you may be interested in various competitions. MIT has different competitions, and if you want to build this device, it's not expensive. This is a $10 to $20 commercially. You can buy one. Okay, and again, the basic concept. Now, in a cheaper device, you see a lot of legs. They are electrical. There are only two electrodes. One is in, the other is out. So electrically, they are connected in series. And in fact, most of these devices are made of opposite type P and N together. A P-type semiconductor, N-type semiconductor. And then in the N-type is the electron carry the current flow, and the P-type is the pulse, the positive charge, right? So when I pass a current, of course, current flow against the electron along the positive charge direction. So you can say that's in terms of device, how it works. They carry heat from one side to the other. And on this side, they reject the heat. On the other side, they cool down. So you can do the refrigeration as well as power production. We show the power. Here is a simple demo of the cooling. Right? That's the ice. You convert the water into ice. Okay, let's look at how the device performance depends on. We show the thermoelectric, three thermoelectric effects, but in reality, it's a solid state material, so there are other effects goes on when I have temperature difference. And the first one is, of course, heat conduction, right? On one side is hot, the other is cold. Heat will flow. This heat could be heat conduction. Electron can conduct heat. Lattice also conduct heat. So you have both electron and lattice. This is different than the Peltier coefficient or Seebeck coefficient. So we have the Fourier law, and if it's a 1D, I integrate it. I get the amount of heat transfer is proportional to the cross-section area, thermal conductivity, and the temperature difference divided by the length. You see this in level 5. And if I group all those parameters together, AKL, I say this is the thermal conductance. We probably defined thermal resistance before, but the resistance is just conductance is just the inverse of the resistance. Right? So this is the definition. The thermal conductance is the Ka over L. And just as a comment, very often we write it, and it just looks like math. But when you actually do it, it matters a lot. Because here, if, for example, the heat flow is inversely proportional to thickness, right? So in the technology development, if I use a film, L is of the order micron, and if I use a bulk material, L could be probably hundreds of microns or millimeters. And that heat flow is a zero order magnitude difference for the same delta T. So whether in reality you have different problems, sometimes it's Q is fixed, right? Like the solar. Solar radiation Q is fixed. And you want to build your system to create a delta T because it's a thermoelectric device, it's proportional delta T. So that's one type of problem, right? There are other cases where delta T is fixed. Give me an example. There are people looking into ocean delta T generation, right? In the ocean, there is the top and bottom temperature difference. So you've got different problems, and you can go back to the most basic picture to think about your system. Sometimes that's always the first step, okay? Now let's look at the device. Again, the real device has many repeat units of this T and N. And if I have just an ideal device, how much cooling I can create? I pass a current, and the cooling is the difference at the junction on the two materials. So one positive material, Peltier coefficient, times the negative material, Peltier coefficient, times current. So that's how much cooling I can create, right? But in real situation, what happens is that when this side is cold, this side is hot, the heat will flow back. This is solid material. You can't get rid of that heat conduction. So heat will diffuse back by conduction. That's one non-reality, let's say non-ideal factor. The other non-ideal factor is when I pass a current through, I have jar heating. I didn't talk about jar heating, right? That's unavoidable part. I don't have a superconductor. In fact, you don't want to use a superconductor here. Superconductor, electrical superconductor, is only one quantum mechanical state. The entropy is zero, doesn't carry heat. Electrons do not carry heat in case superconductor. Okay? So, there's jarring because of finite electric conductivity. And I have to consider both reverse heat conduction and jar heat. Now, if I think about jar heating, the difference between conduction is this side is hot, this side is cold, heat goes conduction. The jar heating is uniformly generated along the lag as approximation. So in that case, jar heating about the half goes this way, the other half goes the other way. Right? You can solve the equation, you'll find that's the answer. But that's the intuitive argument also. So in that case, the real lag cooling I have is in addition to Peltier, I have half of the jar heating, this is electrical resistance, and I have a reverse heat conduction, that's the thermal conductance of the two legs. So, that's the mathematics, the resistance, electrical resistance proportional to the resistivity of both legs, area, length, and here thermal conductance, they both and P and N combined together. Okay? And now you can say the amount of heating or cooling I create depends on the current flow, right? I squared. One is linear, the other is squared. If I drive the device too hard, I generate too much heat. I drive the too little, doesn't have enough cooling. So there's an optimum there. When you drive the device, there's an optimum there. It's easy to find the optimum. But see, I want to find the optimum not only for cooling, but also for efficiency. So I have to calculate how much electrical energy I give in. You say I square R. It's not that simple. There's a little bit of trick here. Because there is an I square R, so voltage drop is I times R, that's the ohmic part. But when there is a temperature difference, there is also a Seebeck voltage, right? So when this side, one side is cold, the other side is hot, there's an additional voltage you have to overcome, the internally built voltage, Seebeck voltage. That's the Seebeck coefficient difference times delta T. That's the voltage you have to overcome in addition to resistance. So the electrical power is I times V, right? So that's the W, that's the electrical I put in. So the efficiency, according to our definition, for refrigeration, we talk about coefficient of performance, right? We don't talk about efficiency. So this is what I want, the cooling. This is what I pay. The pay is the power. The power is the current times voltage. So I have I square R, that's the jar heating. I have to overcome the Seebeck voltage. So that's the term there. So that's the bottom part, that's what I pay. And the numerator is what we derived in previous slides. The cooling is Peltier, reverse heat conduction, and the jar. So now you go to optimize it. And this, yes?
Shouldn't Seebeck the denominator be reversed?
I squared R. No, you wish that's the case.
Huh?
You wish that's the case.
Yeah,
When you have a delta T, you have to push current. You can see, okay, when I have a current flow for cooling, this is T, this is N. I flow current this way. Okay, but this side is hot. The voltage is against here. Okay, otherwise you get too easy your problem. So you go to optimize your current, right? That's the arithmetic. You can P phi Bi equals 0, and you find the optimum current, and then find the optimum, under optimum current, you got to maximize efficiency, or COP. Okay, of course I dropped all the math. And let me again make a comment. You go to say your cooling COP, that's easy because there's no denominator here. You got the optimal current for maximum cooling power. Here, you got an optimal current for maximum efficiency, and the two do not agree with each other. And in fact, in your operation, you want to adjust your current just in between. You can't satisfy it. You go optimal current, you don't have much cooling power. Okay? So the other point is, you look at this, you say, the familiar term, this term is all thermal engine. That's a Carnot cycle for refrigeration. We wrote down Carnot for power generation. But this is a Carnot. So it's a Carnot factor, it's a heat engine. And of course, you want to make sure this term is less than 1. Right? You can't beat Carnot. And here came to this factor Z. That's thermoelectrics. Every time people see you, what's your ZT? This is where it came from. Z times temperature. And this T is the average temperature between the hot and cold side. And this Z, again, this is all coming from this mathematics, doing derivative. And it's the Seebeck difference of the two material. And the denominator is the conductance, thermal conductance times electrical resistance. So you look at it, it's not a material property at all. right? It includes the materials property, Seebeck coefficient, electric resistivity, thermal conductivity, but it also depends on the cross-section area. And then you look at this function, you want to maximize your ZT to get a higher efficiency. So the first thing is that you go to maximize your Z by geometry. You can reduce the denominator by changing your L over A, right? That's the least you can do if you don't work in the material. And that's what you want to minimize. And if you minimize it, it turns out this is what you have to do. The K max R, this is the minimum when the length cross-section area of the two legs. So your engineer, this is where when you build the device, you optimize it. Okay? And when we do that testing in our own lab, sometimes it just involves hand polishing all this, trying to make it match to each other. So you want to get a better performance than others, right? Okay, now you substitute your best case, you do everything ideal, that still is not the ZT. That's still not the individual material property. It depends on both sides, right? P and N type materials. So basically, if I want to make a good device, I need a good N and good P, and the two should match each other. One material, you get you don't get the best performance, right? You can see, and you get about half of the performance if you have a good one material. But because at the end, using the tool means you have to make a lot of choices. In materials research, people just talk about one. Your engineer, you know you have to go to get both materials. Right? Somebody has one good type, you say, do you have another? You're eager to ask. You go to find others who has the other type. So this is when material scientists just say, I discovered material with high Z. That's S per sigma over K. Okay, you want a material with a high electric conductivity. That's you want to minimize jar heat. You want a material with a high Seebeck coefficient. Seebeck coefficient fundamentally is the heat carried per charge. Okay, we'll talk more on that later. So average speaking per charge, how much heat carries. And then you want a thermal insulator, a low thermal conductivity, because you don't want the heat to reverse back. If you know any materials, let me know, okay? People have been searching this for centuries. Good material with good electrical thermal conductivity, poor thermal conductivity. But also, you want every electron to carry a lot of heat. That's the trick. And this has to happen in one material. Same material.
So we derive the Z max for a junction?
Huh? This is the only, Z max, you need you compute a device, you need two materials. Right? Well, theoretically, you don't need two materials. You can do one material. In fact, in that case, what people choose the other material, they choose a superconductor. They just don't do anything. So that's how they characterize one material if you want to do a good job. Right? But see, the point is, in material research, you can't wait to get a two material and you report ZT, right? Get one material take many years. So you do a simple material to say this is a measure of how good is this material. But as an engineer, you want to build a device, you have to say, where's the other material I need? I need both materials. Okay. So those are the comments that is made. You have to optimize, the engineer has to optimize the lag. And you need two types. And you optimize the device performance, load matching by current, right? This is a Kumi. So here is some typical number for for the business telluride, that's the commercial device. Mostly you can only buy this type of material-based device. Seebeck coefficient is about 220 microwatt per Kelvin. Electric conductivity between the phase K, thermal conductivity 1.5 watt meter Kelvin. This is all SI units. It's good to keep in mind, except that micro, so 10 to the minus 6. They put it on the lumber, the ZT is about 1. And we'll talk how good is that. Now, what's the problem? If you have all this lumber, you say, okay, this is, I take a leg 2 millimeter long, electric conductance to phase, cross section 1 millimeter square. So it's a small device. If you look at the device that passes around, that's the dimension roughly. Each leg is only 20 milliohms. 20 milliohms. Very small. You go to buy a resistor, it's actually very hard to buy this small resistor. What that means? It means if you want to build a single leg device or 2 legs, because the current is voltage divided by resistance, right? You push a huge current. You need a big power supply. So you go to look at it, even in your lab, we have big power supply, a small drive, a small device. And at the end, that means cost, so everything you have to consider. And that's why some people do micro devices. You can actually shrink your area, right? You do a smaller cross-section area where you put a lot of those together. In that case, you get a higher resistance by putting more of those legs together. So in our the device I showed the pass around, this is about 100. So if you multiply 100, it's only 2 ohms. The total resistance if you only sell the device like that. So it's a small resistance, large current device. Okay. So that's the reason to put them in series is getting higher resistance so that your power supply is easier. But say it's still a pretty large current, and then you put them thermally in parallel because the carry heat from one side to the other. Electrically in series.
When you optimize your system, then do you really get the simple number 1, 1, 2?
What simple number of
1 millimeter, 2 millimeter.
Oh, you mean no. This you can change. You can make a long leg to test it. You will still get the same delta T. Okay.
Yeah, but when you optimize the system.
Optimize means also material cost. Right, the real world is not, let's say, just you have to match to your application. You don't have to fix to the geometry I pass around, and that geometry is in commercial production because, in fact, each application maybe it's different, but the current of the market is too small, so people are just selling more standard modules. Well, anything you go non-standard, you have to talk to manufacturer and see whether they can manufacture or not. Okay, so this is an example. This we built before. This is actually measuring 2 legs is a lot more difficult than measuring a device because anytime you put a thermocouple there, you have heat loss. Heat loss, so your performance may diminish, right? If you want to say what's your maximum delta T or that, so it's a lot of time to glue in and doing the experiment. You have your leg is milliohms, so anytime you have missing color in solder, the industry they do much more, much better. I looked at the production line, I was really amazed at what an untrained worker can do versus what we can do in the lab. That's the different environment. It's, this is the 1P, 1N, and this is a measurement curve. You can say it's a pretty large curve. In this case, we go one peak along line X going through that device. Right, line X and each leg is about 1 millimeter cube. So this were. And what's amazing is even with that small thing, On this side is 100 degree, the other side is 0. So you can drive it pretty large the heat if you have to. But efficiency is not very good. Okay. The materials is temperature dependent. I mentioned this before. And the analysis I gave you is for constant temperature. So if you do real device design, you have to go solve differential equations and match the property, consider all the temperature-dependent properties. And that I'm not going to cover in depth. Anybody wants to do that, you can read the book. And this is the energy balance in differential form. And this is the heat conduction term. This is the Thomson term. This is general heating term. Okay, so that's a differential equation locally. And very often people use differential analysis to drop the Thomson term. And then the boundary has the Fourier term and the Peltier term. So you have a boundary condition and the differential equation itself. Again, this is beyond what I want to talk in detail. And now let's look at where those technologies are. I have the expression for COP, and you do the same analysis for power, and you get the efficiency for power generation. And the efficiency of power generation again has ZT inside, and this factor is slightly different from COP, but you go to check it, it's probably universal, not one. And this is the power factor, right? Again, it's a thermal engine. The power times whatever your material. If you can drive to power, you win big in this. You have high ZT, you can drive to power, right? And so this is not so, I would say this is not so accurate. I made this slide around 95, 96. And this is the temperature ratio hot to cold in Kelvin. And this is the efficiency. And what I put down here is the thermoelectric is at the bottom. Okay. It's not a rosy picture first. You have to do a lot of research. Right? And the power plant is about 40%. Right? The normal coal-fired power plant is 40%. The internal combustion engine is about 20%, 25%. Right? What I did not put here is solar. Solar depends on amorphous silicon about 6%, single crystalline silicon is about 18%. Once you think about that, then your picture becomes better, right? You can, in fact, say the LASA uses thermoelectric power generator, that's about 6-7% in the deep space missions. But now in the lab, there are people developing thermoelectric generator using ZT about one material. It's around 12 to 14%. 12 to 14% bring you to level that's actually very attractive for some applications. So really, it's application dependent. You don't at this stage we're not thinking it's not at the level to say I'm going to replace major power mover in the sense power plant. You're not even there. With internal combustion engine, but there are many different sources where you can potentially use it. And there is a refrigeration. We've given this before, right? And COP again depends on temperature, right? And COP of thermoelectric compared to household refrigerator is about a factor of 5. So that's actually probably the hardest if you really want to say the application. Say really replacing refrigerator, I think will probably take a long time. But again, there may be other applications where you can think about the cooling. And in fact, the current market, as I'll show later, is mostly in the cooling So this is where really the engineers, you need to say, I know the technology, you say where it makes sense. There are different areas that they could make sense. And commercially, mostly standard size. When standard size, the people offer different size, but the geometry is very similar. The height could be, in the case of power generator, the actual feature about 5-6 millimeter, and the coolers typically millimeter in height in the next. And the top is ceramic, right? And top bottom ceramic. And in between, the legs are interconnected typically by copper. So the technology-wise, they have to put actually diffusion barrier between the copper and the material, because the copper easily get into the material that can poison the material. Okay, in terms of applications, these are more standard small coolers. This is because when you reduce the compressor actually, the smaller you make, the harder, in terms of it's harder to make the heat. When you make a very small compressor, of course, the moving part is powerful, and this becomes more, attractive. Solid state becomes more attractive. A lot of the dormitory hotel refrigerators are made of thermoelectric. And still, the efficiency, I think, is still not as competitive, but the cost could be very attractive. And then it could be as small as just a laser diode. And the people, in fact, put a lot of multi-stage to create a larger diode. Each stage is maybe this highest about 6 stages together. You can create a diode commercially 150 to 160 gallon. So the infrared detector very often needed to be cooled to put those multi-stage into the infrared detector. But many laser diodes has a thermoelectric cooler. This is because the wavelengths in telecommunication, the wavelengths of this laser will drift as the temperature change the wavelength. So they actually use thermoelectric to stabilize the temperature. Not much for the cooling, but for the stimulant. Medical equipment, DNA, when you have to do temperature denaturalization and recycling. And probably a really good commercial example is this company called America. And they started putting a device. This is where you have to look at where it makes sense, right? They started to manufacture around 2,000 thermoelectric cool seats. And in some high-end automobiles, now they have a market of about 2 million modules into the automobile car seats. I still don't have this in my car. It's a luxury item. And but they did pretty well. Quite successful now. The DOE is trying to even get rid of the main air conditioner. And the idea is that the main air conditioner in automobile requires about 6-7 kilowatt. And the purpose is you turn the engine on, air conditioning on, you want to cool the whole compartment in about 5 minutes. Right? But normally you don't need a large compressor. So the question is whether they can use this distributed cooler into the automobile. I'm not sure whether it will be successful, but there is a program like that. And in fact, this is when you think about where they make sense, right? They find the seats, not your office seats. Your office seats you move around. Once you get the car, it's there. They plug in the power because this needs a power there. Right? So, any other places it could be using that? movie theater seats. That's probably too big. I was thinking about the bed, right? But say there are actual products there. You go to. I was thinking before that I looked around. There are products already. I guess the key there is whether it's physiologically comfortable, and also how you reject that heat, right? If you reject it to the same room, does it make sense at the end? So those are all the places where if you're an engineer, you got to think about where it makes sense and where you have a product people accept. And with the more product into the market, of course, there's material is also improvement, and you have further advance the technology. Power generation. The main driver in the past is space missions. So once you go beyond the Mars, the solar radiation diminished. So in Mars, most of the power still come from the solar panels. Although there are thermoelectric generator, and sometimes those generator purpose was actually to keep the electronics warm. Amazingly, right? You go to say beyond it's very cold in the night. There's no power. You need the electrical power to heat up the electronics. So the space mission, most of those deep space mission are thermoelectric power, and that's a good news because Galileo, for example, sent back signal for more than 20, close to 30 years. Galileo eventually the signal was not lost a lot because of power generator, just because the mission was abundant. Voyager, all those were based on thermoelectric generator, and in that they use a nuclear source. So actually, I went to one deep space conference in our project. It's interesting. In the conference outside, there are people, space missions. So there are outside people protesting because most of the space missions are nuclear-driven power. Okay, the terrestrial application. This is a standalone generator. Where, for example, this company, Global Thermoelectric, they've done good business because they sell those power generators along to big oil companies. The oil company needs to monitor their pipelines. The pipelines, say you go through Alaska, there's no electrical power there, so they actually use the oil to generate the heat and do power generation. Body power watch. Okay. I don't think it's very commercially successful. The first company trying to market it was a Japan company, Seiko. I went to visit it. At the time they said $3,000 a piece. It's a body powered watch. I couldn't afford one. But say it's amazing that the watch only needs 1 microwatt. Right? 1 microwatt. That's what I learned from the trip. The temperature difference is 1 degree Kelvin, a degree Celsius to develop for this watch. And there was a lot of companies, Canon, I think. I didn't go to check their watch, but I heard they are still on the market. They're selling $300. This one went to, when I visited, they say, was sent to Smithsonian, so to the history. But I think Canon probably still sell about $300. I don't have much. I don't need a watch. Okay, but some people are developing body power for. You think about the low power electronics area. Right? Some of these devices don't really require a lot of heat. The other day I met an MIT professor in E department. I don't know whether I'm a student there. He said that he can generate a few hundred microwatts, which is pretty good. And I saw Philips trying to also develop it, the body power. And in fact, it might be worth the calculation to say, I think Philips is trying to develop. Where you put the body, the delta T, right? One of the prototype I saw is more like around the head. Maybe it's good if you generate enough power for the poor kids to read it, like an LED now, how much power of LED is. It's interesting to check. And these were actually talked a lot recently. Not because this will create a lot of Seebeck in the thermoelectric generator, but this will be a technology that will really make the pool area people burn. Because look at, say, a lot of places people are still cooking using wood, right? I know where I grew up, say not my place nowadays, but I grew up where I used wood. And in this wood, if you ever use wood cooking, you'll know that the smoke doesn't burn efficiently. And what Philips developed is a fan, generate power from the temperature difference of the burning, and then drive the burning process clean. So it's a clean wood burner. And now I heard that they are trying to market, but they still, this is about $10 to $20, and poor people still couldn't afford it, $10 to $20. And so their market is now first to get to World Health Organization to buy it and give it to the poor people free. So there are a lot of, and this one, if they can get all the people use it, it's a tremendous, their analysis actually, of CO2 problem, right? Because about 2 billion people are out of grid in the world. A lot of people burn those wood stove. And if you make those wood stove efficient, it reduces a lot, significantly CO2 consumption. So the point is, at this stage, you have to think about where it can make sense technologically. Well, at the same time, say, of course, a lot of you are interested in developing more efficient, better materials. So, I go to a lot of material conference, thermoelectric conference, and one sense in the past, the last conference was very different. But in the past, you see more than 90% of the talk on materials. And not many talk on systems. So this is where I think the system, the engineer actually can make a good contribution there. Because a lot of times people just say, I have the ZT, I'll be making a difference. But ZT is only half of the story. Because if you look at a typical system, right, where the cost will come from, most likely it's not in the generator. That's it's an important part, but it may not be the dominant one. So think about this object to be cool. The difference of thermoelectrics from solar is a solar cell you put in the sun, that's your system. You manufacture out, you just need a frame and put there electrical, and the rest is it's about half the cost, right? Balance of system. The inverters, all those other stuff. But it's a much simpler system. Here, for thermal system, you have to establish, you have to be able to maintain the temperature difference, right? So that means you have to take the heat out or put the heat in. And I once did a calculation for a system, and what I found is the thermoelectric material is only about a few cents per watt electric. But the costs come from all the aluminums that, I didn't do a very good thermal design, but that costs a few dollars per watt. Okay. Because how you maintain the heat sink and do the cooling could be easily dominant in your cost. Not always, you have to do a good design. And the other is, if you think about the temperature, right? So you need, for example, household temperature is about 22. Think about your refrigerator. And inside the refrigerator, let's suppose you want 0 degree. So you say, I need a 22 degree delta T. But that means your 22 is your refrigeration compartment inside, your air outside. Now you have to transfer that heat to the cold side. So this cold side must be lower temperature than 22, right? So let's suppose 15 degree. I give few degree delta T. And then the hot side, I reject the heat. You don't want the heat reject has to go to the air. So I have to have another delta T from here to here. I give another 5 degree. Okay, that's 12 plus 22. So I need a 39 degree rather than 22 degree. Now you go to 39 COP versus 22 COP will be very different. Right? So your system is really a very critical part of the consideration. That's the significant difference of those thermal systems. It could be more expensive than the thermoelectric side. Same thing if you think about automobile, right? The automobile, let's suppose you want, this is a hot gas, and they put the thermoelectric here, this is the exhaust, and then you cool this side. And you see what temperature this system will operate. Let me suppose the device operates at a uniform temperature. Not a good design, okay? But say, I suppose a device operates at uniform temperature. Then the hot gas must have a higher temperature as it exists. This temperature of the gas must be higher than this TH. Otherwise, heat cannot go from gas to the hot side. Right? Heat only go from a high temperature to lower temperature. So that means if the gas is 600 degree, the amount of heat I can take out is from 600 degree to whatever this temperature. So if you do optimization, it's about half. Because you need to take that heat out of the gas, put it into the device. So that means your hot side may be operated at 300 degree. Right? So you can't do your calculations based on 600 degree delta T, what's my COP, what's my efficiency. And now, of course, you can be more innovative. You say, okay, I don't operate at the same temperature. Each section I operate at a corresponding higher temperature, and my efficiency, system efficiency will be higher. So there you got a lot of the system design. It depends on material availability and cost, weight, particularly when you do automobile. And with weight and cost is everything. And so a lot of really, so there, what I say is there's space for both sides. There are a lot of problem engineers can make an important contribution, and a lot of problems so the materials ZT improvement can improve good contributions. Right? You look at say this is not a serious work now in the automobile side because you look at where you potentially use it. But maybe power generation, most people now looking at the catalytic converter because radiator quality is too small. Okay. And the reality is, the automobile company says 3% fuel saving. They'll be happy to think about it. 3% fuel saving is less than 1% system efficiency. Okay. So if automobile exhaust is 1/3 of the waste heat energy there, 1/3, let's take half of the heat. If I can intercept half of the heat, so that's 1/6. So my system efficiency, if it's 6%, which usually can be done using steroid from not system, just device, maybe 6%. Right? But then the question is, when you put all this together, your hot side, your cold side is radiator temperature is 100 degrees now. But you internalize not good. You have to think of all this to put them together and make you have good feedback. Okay. Yeah, so the BMW is very aggressive since whether they can put in the market when home
I talked about this before, industrial use case, renewable. And it's really up to you to find them where it could be possible. It's not competitive against IC, not competitive against main motors. Let's say there are a lot of places where it could be. Okay. Any questions?